This presentation is delivered by the Stanford Center for Professional Development.
All right. Well, let's continue. So the next topic is generalized inequality constraints. By the way, as I said, I know we're going quite fast over this material. We're going at about twice the speed I think we should be going. But that's fine because things like the generalized inequalities, we're going to be using these in applications basically from now on. So you're going to get weeks and weeks and weeks of seeing real problems that use these things. And so if it feels like we're going too fast right now, we are. But you'll have like 4 weeks in the context of applications to absorb all these things. Okay, so let's get back to our breakneck pace. So generalized inequality constraints. So here, we're going to generalize the inequalities. By the way, later, we're going to generalize the objective. That's actually in some ways more interesting, or it's a more significant generalization. But right now, we're going to generalize the inequalities to be vector inequalities. So here, fi of x until now has returned a scalar. And it was fi of x is less than or equal to 0. We're going to actually, we're going to have fi of x return a vector. That's a vector inequality. And it's defined by this cone ki. So in this case, if fi is ki convex, so it is a convex function with respect to this cone, this generalized inequality, then this is called convex problem with generalized inequality constraints. And you can generalize almost everything you've seen to this. I mean, for example, the set of optimal points for this problem is convex and all these kind of things. Everything just goes through here with this. But in fact, there's a special case that is going to be more important than the general one. And it turns out it's interesting. It's a very special case, but it turns out to be, in some sense, also the most general case. And that's this. It's a so-called conic form problem. And you'll hear a lot about this people have heard a lot about it in the last 5 years. You'll hear a lot about it. Actually, I don't think it's that interesting, and I'll tell you why in a minute. But let me show you what it is. You'll hear a whole lot about it. It's a very special case. Everything is affine. So it's the equivalent of a linear program, basically. In a normal optimization problem, if every function is affine, you have a linear program, because you minimize an affine function subject to affine functions less than 0. Those are conventionally called linear inequalities. Affine equality, that's just conventionally called linear equality constraints. So here, everything is affine. You minimize a linear function. Of course, there's a constant, makes no difference. You don't need it. It's the same problem. It's not quite the same problem, actually. It's clearly equivalent. And that's subject to, now this is a very, very interesting inequality. It's actually, this is affine. And this just says that fx plus g is less than or equal to 0 with respect to this cone. That's all. So this is called a conic problem, a cone problem, something like that. You can type this into Google, a cone problem, and you'll get tons of stuff. I think it's interesting because it sort of generalizes the idea of linear programming to cone programming. If this inequality here is with respect to the non-negative orthant. So recall that if we erase this, that's the default. The default inequality between vectors is with respect to R plus, and it means component-wise inequality. That's a general LP. That's a general linear program. So cone programming, I think, has caught on for several reasons. Actually, it is actually interesting to look at it. But it's caught on for a lot of reasons. First of all, if you're trained in traditional operations research, you grow up, by the way, which is not me, just so you know. But if you are trained or subjected to, maybe that's another verb one could use, a traditional training, everything you'll hear will be about linear programming. So just everything is linear programming. Linear programming, what were you? Oh, okay. So linear programming, everything. So the nice thing about cone programming is all you do is you write this little k down there. By generalizing the cone from the non-negative orthant, you now have something that looks like linear programming. So if that's your training and background, it's deeply familiar. You've had 3 classes on it. And now all you do is you generalize this, and it means that everything's going to be familiar and so on. And naturally, that's what happens. A lot of things are familiar. That's the first reason I think it's caught on. But the other is I think also interesting, and you have to watch out for it. It's this. It's caught on because, in fact, the most highly developed solvers, we're going to go into some detail in this in the last third of the class, the most highly developed solvers for convex optimization problems actually are conic solvers. So people who work on solvers naturally think that cone programming, conic programming, and things like that is this huge, it's this huge important topic that everyone would be interested in. Actually, like linear programming, it's not. Okay? It's actually not. It's very important if you work on these things, fine. But for people who use these things, it's not that important. It's important in the following sense. There are a lot of interesting problems people really want to solve that transform to conic problems. Then, all the people who work on the cone solvers can use their super fancy primal dual homogeneous, blah, blah, blah methods to solve them. But in some sense, that's not anyone, that should not be the business of the general public. That should be the business of this small group of people who work on cone solvers. I'm saying this, by the way, because there's a lot of people who work on cone solvers who will see this tape, and I just wanted to insult them, that's all. But I hope it worked. I'm sure it did, actually. Okay. All right, so this is a conic form problem, and in fact, the one you will see most. Question? There's a question.
I was wondering why there's an I subscript on the K in the first. Is
Oh.
that because you can do different cones in the same set of constraints?
Yes. So the question was, why the I in the K? And the conjecture was it's because you can have different cones for each constraint.
You couldn't generalize it to make.
And my answer was yes.
So it just seems like you could generalize it all to one cone, the highest order cone or something like that.
Yeah, you could do all. I mean, you could do all sorts of things. You could lump these all together and make it one inequality with one cone, which is the direct product of all the cones. Yeah, so you could do lots of things. We'll see that. Okay. Now in conic program, what you'll see the most is something called semi-definite programming, and this is actually interesting. Well, it depends. What you'll actually see is a combination of two types of cone programming, which we'll see in a minute, which I'll talk about in a minute. So semi-definite programming, this is relatively new. So this is maybe 15 years old, but like everything else can be traced back into the 60s, although people had absolutely no idea how to solve SDPs. So, I mean, as a specific example, I worked on SDPs before, in fact, the name had been determined, had been actually fixed in the context of control and things like that. And we were very, very happy when we could solve like tiny little, tiny small ones in an hour. Boy, we were really happy. Anyway, it didn't occur to us that in fact you could solve them like 1,000 times faster and things like that. And that, well, the current state now would have been just unimaginable 15 years ago. So this is an area, and now it's actually very interesting. This has sort of made the transition in the last few years from this kind of esoteric thing a few people in research worked on to just kind of it's just all over the place. It's very fashionable, and so you're supposed to, I guess everyone's supposed to know, and a lot of people do know about it now. It's also used commercially, I should add. So in areas like finance and stuff like that, it's kind of widely used. Okay, so semi-definite programming, or SDP. It's very, very simple. It looks like this. It looks like a linear program, except for one generalization. So we minimize linear function, linear equality constraints. That's so far linear programming. Here's the difference. There's an inequality, and it's a matrix inequality. These are symmetric matrices here. So this thing here is called an LMI, or linear matrix inequality. So that's what this inequality is here. This inequality is with respect to matrix ordering. Okay? It means the left-hand side is negative semi-definite. That's what this means here. So that's what this inequality means. By the way, you'll hear all sorts of other. By the way, a lot of people will write it this way with the straight ones. That's fine. You'll see that notation. And I'm trying to think of some other formulations you'll see with this. Let's see. Okay. Yes. You'll hear people say that this inequality with matrices, that's the loner ordering or something like that. So there are people who try to dress this up and make it fancier, sound more sophisticated than it is. By the way, it's quite sophisticated. A matrix inequality is very complicated. To say that a matrix is positive semi-definite or negative semi-definite here is actually a very sophisticated inequality. So from that point of view, they're right. It is sophisticated, but sophistication doesn't come because you have a name attached to it or whatever. So This is an LMI, and that's it. Now, there's an interesting thing, here as drawn, there's only one LMI. Of course, you could have multiple LMIs. But the fact is, if you have a whole bunch of LMIs like this, if you have two, you can lump it together into one. And you lump it together into one by simply making a block diagonal matrix here with the LMIs. Because if I have a block matrix and I say that the block matrix is negative semi-definite, it just means basically each block is negative semi-definite. So we can just, that's why we can, without loss of generality, work with just one LMI in general. Okay. Now, semi-definite programming is a generalization, actually, of everything you've seen so far except geometric programming. So let's see how. So it's a proper generalization of linear programming. So how do you represent this linear program this way? Now, this inequality here, this one here, that's a vector inequality. So this means element-wise. Okay? Well, how do you write that? Well, it's kind of stupid. If you take diag, this is the diagonal matrix with this vector on the diagonal. A diagonal matrix is negative semi-definite if and only if all the entries are non-negative, right? Or non-positive. So this is the same. So that's an SDP. So in fact, some people would even call an LP something like a diagonal SDP. Fine. Okay. But actually, it's more interesting. A lot of. Oh, and by the way, when you represent a problem as an SDP, it's called an SDP embedding. So that's and these are interesting actually for lots of reasons. The first is, of course, just sort of theoretical. It's nice to know that you have a problem class that subsumes other common problem class. It's nice to know that, in fact, you didn't really have to know about SDP, LP, SOCP, quadratic programming. You have a question?
But if you want to solve a linear program, are you going to solve it with a linear program solver or with an SDP solver?
That's a great question. So it depends. If the SDP solver, and we're going to talk about solvers later in the class, depends how sophisticated the solver is. Okay? If any modern SDP solver would actually be perfectly happy to be, if it handles sparsity, and it looks at AX minus B here, diag AX minus B, and realizes it's diagonal, it will have no loss compared to solving it as a linear program. So that leads me to my second point, is that actually SDP embeddings actually also have substantial practical use. Because if you write an SDP embedding of a problem, it means that that other problem class can be represented in SDP, and it means one SDP solver can do everything for you. Now, very roughly speaking, that's what CVX does.
But is it because it's a linear program, so it uses the linear program solver, or is it?
No.
Because it says SDP is general.
Absolutely not. You can't, because it's going to be a mixture of LMIs, all these constraints, and it cannot call an LP solver. It does not call an LP solver. Will not call it. So it's absolutely not the case. For example, in CVX or any of these other tools, if you write something that happens to be an LP, it does not call a different solver. It calls exactly the same solver as if you'd written an SDP. Okay? So no difference. Okay? Okay. So the point there is an SDP embedding actually then has a practical use. So it means, and it's actually it's so expressive, I think that's a good way to say it, SDP is so expressive that it can be used to represent a huge number of constraints. And for example, and functions and things like that. We'll talk more about that later in the class. I should say also that it's come up now in theoretical computer science. I think it's in lots of areas. Actually, I think we just found out that SDP traces back with a different name into some calculations in physics and chemistry in the 80s or something like that. So, and it goes back into control in the 60s and things like that. So it's got a long history, but that long history didn't really particularly come with good computational teeth. So it was just, it was basically just theory. So that's changed. It's now, this SDP is now not just theory, as I guess you all well know. If by the time you finished homework 3, you will have solved, whether you know it or not, a lot of SDPs. We'll get to that later. Okay. Here's a more interesting embedding, is SOCP. So second order cone programming, the question is, how do you represent this as a linear matrix inequality? Now this is highly nonlinear and it's non-differentiable. And the answer is this, and this is something, we'll see more about this later, and in fact we have something queued up for you, not on homework 4, but on the next one, I think. And this comes about, this is a matrix here, which has got, that's a block, this 1-1 block of the matrix is a scalar times the identity. Now, actually I don't know how many people remember about Schur complements, but let's just say we, the teaching staff, will remind you about Schur complements soon enough. But a block matrix is positive semi-definite. Now this is rough, so this is not quite right. It's positive definite if and only if the diagonal entries are positive and if something called the Schur complement is positive. And the Schur complement is is this minus this times the inverse of that times that is bigger than or equal to 0. Now, in the case for this particular matrix, that says Ci transpose x plus di, like this. Let me put these together. Maybe if you could go down the pad here and maybe you can capture both the big element, this one, and that one. There we go. Okay, yeah, if you can just capture this and what I'm writing here. It's this must be bigger than or equal to this thing. I hope I'm doing this right. Ai x plus bi transpose times the inverse of this guy. Well, that's I inverse. I'll just leave as I. Well, sure. I'll just put I inverse here. Why not? And then that's a scalar, so I will put that down here. I'm using a loose parsing here. And then times aix plus bi, and that is that term. Okay? So everybody see this inequality? So this one has to be positive because it's the last diagonal entry in a positive semi-definite matrix. It can't be negative, that's for sure. So this one I could square and put it over here. Okay? So I can multiply both sides of this inequality by that. I can get rid of all this. I get this. And now I take the square root. Now when I take the square root, I have to be very careful. I can only take the square root here if I know Ci transpose x plus di is bigger than or equal to 0, but it is. And I will get exactly this a second order cone constraint. Okay? So this is an example of how this works. So people call this an LMI representation, an SDP representation. You'd find a lot of stuff on that. And that stuff is interesting, as I said, for theoretical reasons. It's cool to see the shocking number of things that actually have an LMI embedding or an SDP embedding or whatever you want to call it, LMI representation. But also, it's quite practical because it means basically you write down an LMI embedding, then in 3 minutes you can write a CVX compatible function, for example, that will now handle that function just immediately. Okay, so that's sort of the idea here. Okay, let's look at some other problems. Here's one. Here's eigenvalue minimization. So let's do eigenvalue minimization. So here I have a matrix that maybe if you go down to the pad here. There we go. So here, if you have a matrix which is an affine function of a vector x. So an affine matrix valued function looks like this. It's a constant matrix. These are all symmetric. Plus, and then a linear combination of symmetric matrices here. And I want to minimize the maximum eigenvalue of that matrix. Now, let me just point something out. That's a really complicated problem, right? Because you take this matrix. Now, so far, it's fine. Every entry of this matrix is an affine function of x. But now, to get the maximum eigenvalue, you form the characteristic polynomial. It's got n factorial terms in it or something like. It's insane. It's huge. So you don't want to see it. You can't see it for a 15 by 15 matrix. Okay? You don't want to see it. You get some huge polynomial of degree n, blah, blah, blah. If n is bigger than 5, there's no formula for the roots of that polynomial. Then, despite the fact you have no formula for the roots, you now have to select the largest of them. Okay? Now, that can switch. As you mess with a matrix, the second largest eigenvalue and the largest one can kind of go like this. And when they switch, this function is non-differentiable. Okay? So, I just want to impress upon you how complicated this function is. It's very complicated, this thing. However, we can write it. It's non-differentiable, it's highly nonlinear, and so on. Now, on the other hand, we can actually optimize the maximum eigenvalue very easily as an SDP. It's totally straightforward. It's just this. You minimize t subject to a of x is less than or equal to ti. Now, to write this in this full form, I guess, these things I'm not going to do, but you write it this way, right? And this is indeed affine in the variables x and t. That's this thing. So this is the actual L, but people just write it this way. It's fine. Okay, so that's so eigenvalue minimization is quite straightforward. Just so you know, this is something that, I don't know, 20 years ago, no one knew that this was straightforward. No one. 10 years ago, a few people knew, and so on. So this is not this is new. This is not LP. We're not talking LP anymore. We're not talking stuff from 1953 anymore. This is recent history. It's true that a lot of people know that semi-definite programs are tractable. Maybe fewer know that, for example, minimizing the maximum eigenvalue is. Okay. Let's look at another one, matrix norm. Now, matrix norm also, as you know, is a very complicated function. After all, it's the square root of the largest eigenvalue of A transpose A. Now, when you look at this, you immediately know you got a problem here. Lambda max, well, we know that's a convex function. We know that, right? Not only that, we know it's sort of SDP representable because we just showed how to minimize the lambda. But the problem here, this is essential nonlinearity. This is quadratic. And in an SDP, which after all has as its constraint a linear matrix inequality, you got the word linear in it. You're not allowed to have products. This has products here of A with A. Okay, so you have xi, xj terms. That's not linear. So the question is, how do you turn a non-linear problem into a linear matrix inequality? And again, it's an SDP embedding. So you take a larger SDP. It's larger, but it's actually going to be now affine or linear in the variable. So let's see how that's done. It's done this way. So you have to study this matrix quite carefully. And like I say, you'll get practice on this. Not this coming week, but the week after. It's in the queue. We're getting it ready for you. So looks like this. You have this block matrix here, and this is Ti. And you want to know, when is this matrix positive semi-definite? Well, it's basically, you have to have Ti positive. I'm just going to do the Schur complement here. And the other condition is that Ti, now I'm going to do the Schur complement. That's bigger than, this thing is bigger than A of x transpose times the inverse of that. That's, I'll just put divided by t, because the inverse of I is I, times that. Okay? And very important here, that is a matrix inequality. Here. So I should squiggleify it a little bit more. There. Okay? There. T is positive, is non-negative. So this t can go over here safely, like so. Now you take a look at that, and you realize we're quite cool, because because t is non-negative, I can write this as ti, or whatever. I can write it as ti is bigger than, well, no, I'll leave it this way. I'll say this basically says that t squared times the identity is bigger than this matrix in a matrix sense. That means that all the eigenvalues of this matrix are less than t squared. Okay? That means the maximum eigenvalue of this matrix is less than t squared. But the maximum eigenvalue of A of x transpose A of x is the maximum singular value of A squared. And you take square roots and you're back to this thing. Okay? So that's the embedding. Okay. Okay, so that's that. You'll see more of this. I just wanted you to sort of see it now. Also, it's interesting to see. You don't have to know the details yet. Later, you will. That if you're actually curious about what CVX is doing, of course, it is, after all, you can look at all the source if you like and find out what's happening. But if you look deep enough in it, and then ignore all the silly testing and cases around there, the essence is every function implemented in CVX is an LMI representation. That's not quite true. In fact, maybe let me just say a little bit about that. Just I don't mind lying, but let me just, well, I mean, I don't do it that often, and when it's for a good cause, it doesn't bother me at all. But I'll just make this a little more accurate. It's not a total lie. So if you actually look at what cone solvers really do, and it comes back to your question, to be honest. So the question is, if you go to Google and you type cone solver or something like that, or if you look, you'll find all the basic ones. You'll find there's 20 or 30 by now. There's Mosaic is a commercial one. There's a commercial. There's a commercial one actually that you can get in Excel. I mean, so it goes on and on, all these different things. But they all kind of do the same thing. What they do is they solve a conic problem, which is like min, note the period, C transpose X, subject to, and there's many ways to write it, but we can write it. I'll write it this way. Sorry, let me do it another way. Sorry, I'm going to write. I'll write it the same way. I'm going to make these lowercase. Something like that. Okay? So it's, and you know, you can put an equality constraint here. That doesn't matter. Okay. See, so they solve problems like this. Now, here I have to, let me put a J up there. I have to interpret these, and now I can put a KJ here. Now, these Ks can be, and here are the Ks you can have. They're typically sort of R plus, so that's linear inequalities. Okay? They can be second order cone or Lorentz cones, so they can be SOC of some size, K, or something like that. And they can also be sort of linear matrix inequality or PSD cones of size K. So this is really what they look like. Okay. As to whether the linear inequalities and the second order cone inequalities are then further dumped into matrix inequalities and solved is actually a question of semantics and things like that. So we'll leave that out. But this is in fact really what if someone says cone solver, this is what they mean. Now it's actually not, this is not that interesting to people who want to use these things. I mean, I don't know what this would be like. This would be like looking at a very low level LA PAC code and looking at the full calling sequence. It's of great interest to people who write low-level code. It's very important that it be done right, that smart people thought about it, implemented it, you know, and all that kind of stuff. That's true for LAPACK. But not all of us need to see the 14 arguments that you call, you know, DGESL with or something like that. Most of us are perfectly okay with just kind of a backslash or something in between, like in a Python or something where you'd actually let somebody else deal with all the sort of the memory allocation and the and passing pointers and all that kind of stuff. So I think this sort of has that flavor of this cone solver. So now I've been honest about what an actual cone solver in practice is. So okay, all right, let's move on. What we're going to do now is we are going to generalize the objective to be a vector. So far, we left the objective as a scalar. Now we're going to, and we generalize the inequalities to be vectors. And you get things like cone programming, all this kind of stuff. Now we're going to do the objective. And this is a different thing altogether. This is a very different thing when you change the objective. Because now, you have to actually redefine the semantics, because first of all, it doesn't even make any sense. So the first thing you have to do is say, what on earth does this even mean? What does it mean? What if f0 of x is a vector with two things? What does it mean to say minimize a vector? Okay? Well, and you get all sorts of nonsense about this. So it's actually important to get all the semantics right. So a convex vector optimization is just like this, except f0 of x is a vector, and there's a cone associated with it. And let me tell you let me just say what this might mean. Let's do the scalar case. So here, let me tell you the semantics of scalar objective optimization. It goes like this. The semantics is extremely simple, and it all comes down to the following. If you have like 3 people come up with a proposed x, I'll tell you everything you need to know about the semantics of scalar optimization. 3 people come up with an x. I look at the first x, and I check the constraints. If any constraint is violated, in the slightest, I dismiss that x and that person. Right? It means it's completely unacceptable. Okay? And they can't say things like, it was almost feasible or something like that. They're dismissed. Okay. Now the remaining 2 people both pass the feasibility test. Their x's are both feasible. They meet the constraints. They haven't been dismissed. How do I judge between them? Well, I mean, it's extremely simple. I evaluate the objective function for those 2 points. Okay? If one is less than the other, I say, that's better. And I dismiss the other one. Because here I have I have two potential solution, two potential points, each of which satisfies all the hard constraints. This one is better on the objective. Now, if they're the same, then the semantics, actually, what is the semantics if they're the same? Yeah, they're both, no, they're not both optimal. I didn't say they were optimal. They're just the same. So the answer is, as far as that problem is concerned, you actually don't even have a right to have a preference between one or the other. You don't. Okay? So if you look at that and you say, oh no, I much prefer this solution, then your objective is not reflecting your interests and your utility function or whatever that's what they call it in economics and finance, or your cost function in engineering or whatever. It's not properly, if you like one more than the other, but the objectives are the same, your modeling is not right. Everyone see what I'm saying here? So that's it. Now, the key to this in the scalar case is easy because an objective comes out to a number. It comes out to like $17 of cost per unit. In which case, 16.38 is better than 17, period, if it's a cost. If it's a revenue, it switches. Okay? So the point is that they're all comparable. Now suppose they're vectors. Now, they're vectors, as you know, with vector inequalities, they're not linear orderings. Linear ordering is one in which any two elements can be compared. That's one of the nice parts about R. There are linear vector orderings. Wait, did we assign that problem? I think maybe we didn't. Does anyone know a linear vector ordering? This is just for fun. What?
Lexicographic?
Alphabetic, yeah. Or lexicographic. Someone else was going to mention something. Same thing? Yeah, okay, so lexicographic. Lexicographic ordering on a vector says you look at the first entry, you get two vectors, you look at the first entry, and if one of the entries is bigger than the other, done. It's higher in the ordering. If they're equal, you drop to the second. And then you see who beats on the second. And if they're equal, you go to the third. And so on. And if they're equal all the way through, then the two vectors are the same and there wasn't really a question anyway. Right? So that's lexicographic ordering, and it's a total ordering or a linear ordering is the name for that. It means any 2 points can be compared. This is why dictionaries work and blah, blah, blah. Okay, so. All right. Most orderings of interest are not total orderings. Most vector orderings, of course. The ordinary ordering on R is, of course, a linear ordering. But most vector orderings are not. And in fact, that's exactly what makes it interesting. So, for example, in matrices, for example, when you're talking about confidence ellipsoids, and you say, which is better, this or that? This estimation method has this confidence ellipsoid, this one has that one. Which is better? Well, of course, it can happen that one of the ellipsoids fits in the other one, in which case you can say, I like that one better. But of course, you can have this thing where they're not comparable, where neither ellipsoid contains the other. And then you have to say something like, this algorithm actually is better at estimating, azimuth or whatever than elevation. This one, on the other hand, is better at doing this than that. So that's the idea. Okay, so this is just to get the rough idea here. Okay, so we actually have to figure out what is the semantics here. Well, the way this is done is you look at the set of achievable objective values. Okay, now that's a subset of a vector space of dimension bigger than 1. I mean, we're assuming that's the case here. You look at the set of achievable values. That's the set of objective values you can possibly get with a feasible x. And now you say the following. It's very simple. You say that a point is optimal if that achieved objective value is minimal in O. You say it's Pareto optimal. Sorry, I said minimum. I meant to say minimum. If it's minimum. It's Pareto optimal if it's a minimal value. Now these are, you probably don't remember these from long ago. But the ideas are this. A minimum point of a set is one where every other point in the set is comparable to it and larger. That's what a minimum. So this is a minimum point. If this is the set of achievable objectives, this is a minimum point. So here you'd say that this is the only case essentially when you can say unambiguously this point is optimal. It's the only time you can actually say minimize something and say x solves this, because no one could possibly argue with it here in this case. This is minimal. This is minimal with respect to R plus 2. this point is optimal. Minimum, sorry. Okay. Minimal is this. Minimum means you're better than every other point. Minimal means no point is better than you. Now, of course, if in total ordering, these are basically the same. They're the same. But the difference here, you can have points. So if you look at this point here, all of these things are honestly beat by this point. They're honestly beat by this point because they're comparable to this and they beat the objective, period. That's this point. But these things over here are interesting. These over here are interesting. So the things in the second and fourth quadrants, they're not comparable to this point. They don't beat it. Any point over here would beat that point unambiguously. And the whole point about being Pareto-optimal or minimal in this set O is that there are no such points. That's the definition of being Pareto-optimal. So you would say, in fact, if someone said, yeah, well, what about that point and that point? You would actually say that they're incomparable, that neither one is better than the other. And you would say, in fact, that in discussing the two designs, there's a trade-off between the two. You can trade off one objective for the other. Okay? So this is the picture. I mean, some of these ideas are kind of obvious, and you've probably seen them before in other areas.
So on that curve, it's a significant portion of that curve also Pareto-optimal.
Yeah. You see this little thing in here? Yes. That's not Pareto-optimal. Okay. And actually that point, although you couldn't possibly see it, certainly at video resolution you can't see it, or can you? I don't know. It's somewhere right around one line width. Anyway, this point is open, and this point is actually filled in. So these are Pareto-optimal down here, and all of these are, right? So, and I mean another name for Pareto-optimal is not stupid. That's another technical term, right? Because, for example, if someone says, "Yeah, well, that's my choice," okay, the technical name for that is stupid, and the reason is this: if you go down here like this, you know, everything like this, anything in there is a point that unambiguously beats this. So, for example, and it doesn't even matter. So the point is, it would be stupid to choose this point. Any of these other points in here would actually be comparable to that point and unambiguously better. So that's the other way to think of it. It's just not stupid. But the way to do it is very simple. It basically says, you know, minimal means you look up in here and you want everyone else to be up there. Those are the places which are unambiguously worse. And Pareto-optimal says you look down and left. I mean, this is in this very simple case. You look down and left, and you want to make these are all the places which are unambiguously better than you, and you want to make sure that no one is unambiguously better than you. So that's it. And you've seen this idea many times. My guess is you have, or even you've thought it, just didn't have a name for it or something. So, all right. Well, vector optimization comes up in essentially only two practical contexts. One is where the ordering is with respect to matrices. And that's where you're comparing. And that actually comes up all the time. It comes up in like experiment design. It comes up in estimators and things like that, where basically the objective is something like a covariance matrix, like an error covariance matrix. Everybody wants a small error covariance matrix. It defines an ellipsoid. Everyone wants a small confidence ellipsoid. That's clear. The problem is those are not totally ordered, right? So, and we'll talk about what happens in that case. So that's the first case, is when these are matrices. That's sort of a subtle case. The other case is actually much simpler, although it comes up maybe more frequently. It's just multi-criterion optimization. And here the cone is nothing but the orthant. So here, basically, it's called multi-criterion optimization. Your F0 has got a bunch of components. And people call this a multi-objective problem. That's another name for it. And you will hear a lot of nonsense all put up around all this, where people will say, so you'd hear people say, and of course it's true, you'd hear people say things like, oh, all optimization problems are multi-criterion. Well, like, duh, so what? I mean, that's completely obvious. And we'll see that it relates immediately, if you know what you're doing, to ordinary optimization problems. So, We'll get to that in a minute. So in a multi-criterion, you have multiple objectives, and if you want to think of something specific here, you might think of an engineering design, let's say a circuit, and one of these would be something like power, one would be delay, one would be area. I mean, just for example, okay? Or this could be some control system or something like that, and one of them could be, again, something like power. One could be how close you're tracking, and the other could be something like the roughness of the ride. The point is, there are multiple objectives, all of which you want small. And of course, once you think about it, you realize almost everything has this form, okay? In an estimation problem, you'd say, well, I want something that matches my observed measurements well. I mean, it would be foolish not to have something like, but at the same time, I want an image that's smooth, for example, or I want one that minimizes some, that is simple in some method, in some sense. Those are all going to be multi-criterion problems, so estimation problems, pretty much everything. Okay, and I'll say a little bit about how it all fits together in a minute. Okay, so, roughly speaking, the idea is here you want all of these small. Now, the one thing you can say is this: if someone comes up with a point, and you beat someone else on all objectives, or I should be more precise, if you beat them on all objectives, if you meet or beat them on all objectives and beat them on one, you're better. Everybody got that? So, I mean, actually, and this is like a core in economics. You go through all of this, and I mean, you'd see all these things. That's what it means to be better. So Pareto optimal means no one beats you. That's Pareto optimal. It means it means basically if you have two Pareto optimal things, you have to have traded something off. They have to beat you on something, you have to beat them on something else. Period. Okay. Now, Pareto optimal, well, it says exactly that. It says that if one thing is less than or equal to the other, the same objective, that's in a vector ordering, then they're equal. And if you have different Pareto optimal values, there's a trade-off between the objectives. And the classic thing from least squares or anything else would be something like this. So you'd write it this way. You'd say minimize with respect to r plus squared. I mean, it's a bit of a pedantic way to write it, but it is actually exactly what you mean. You say, please minimize with respect to the second order orthant the following. Two objectives, both, by the way, convex here. Norm ax minus b squared, that's like a matching criterion. That's how well do you match something. But at the same time, please do it with a small x. Okay? How do you judge such a problem? Well, what you do is this. X, by the way, could be in a vector in 10,000 dimensional space. But in fact, there's only two objectives. So in principle, what you do is you check every vector in R10,000. So you plug in every possible x, and you get a score, which is a pair of numbers, non-negative numbers, and you put a dot at every single point. This is conceptually. You now do this for all 10,000 points, and you get this shaded plot that looks like that. In fact, it's some kind of a hyperbola or something. It doesn't matter what it is, right? Now, also, I should add that O has some interesting structure out here, but it's not interesting to us. So in fact, O doesn't. This thing kind of can look like this, okay? Like that. And then you might ask, oh, see, you can't even achieve that point. That's not interesting for us. Because what's interesting for us is down and to the left. That's the only thing interesting to us. And therefore, whatever O looks like up here is actually of no interest. Now, unless it kind of does some weird thing and wiggles around and comes out down here. But it doesn't, okay? O is in fact, O is a convex set in the general. Sorry, it's not a convex set. Sorry, I scratch that. Okay, so we're only interested in what's down and left. So the actually only thing that's interesting here and is what's shaded here is the Pareto optimal curve. Now you saw this if you took 263. You saw this, and this is This is called the regularization. This is regularization and so on. So you've seen all this, and these are the Pareto optimal points. This point, or there could be of course multiple x's that give you that, but in any case they all have the technical attribute of being stupid. Because there are lots and lots of other x's that beat them as better fit, smaller x. Okay? This point here is very interesting, possibly desirable, irrelevant, because you can't get there. Actually, this one is also technically stupid. In fact, I guess this is even, I would say the technical term for this is quite stupid. And let me justify that. It's quite stupid because, first of all, there's better points. That's number one. Number two, it's not even achievable. So that's why it seems to me it's even worse than stupid. But anyway, so this should be clear. Okay. Here is a very famous one. It's things like the risk-return trade-off in finance. Okay. So, and we'll look at problems like this just as a kind of a generic example. It looks like this. I have two objectives, and let me explain the problem here. So the problem is this: I have a vector that represents an investment portfolio. So xi, for example, might be the fraction. People set this up differently, but a classical one is this: xi represents the fraction invested in asset I. So you have n assets. Negative, if you want to have negative, I mean here we've ruled it out. But the point is, if you want to have negative, it means you have a short position. If that asset is cash, it means you're margining. You're doing stuff on you're borrowing money to finance the purchase of other assets or something like that. So, but here, to make it simple, we've just made x positive, and this you'd say there are no short positions. And if one of those assets is cash, you'd say no borrowing, no margining. Okay? So that's the idea. That's the fraction. And of course, as a fraction, it's got to add up to 1. Okay. Now, what happens is here is you invest in these assets. There's one period. And what happens is there's a return, or the prices change. So you could call P, it's a vector of relative asset price changes. So for example, it might be something like, I mean, it doesn't, and you can even make it, it doesn't matter. It could be like, plus 1%, plus 12%, minus 7, or something like that. It means that the first asset went up in value 1%, the second 12, if that's the number I said, and the other one went down, I forgot what I said. Whatever I said. That's the idea. So if you form P transpose X, that gives you the total return on your portfolio. Okay? Now, obviously, if the returns were known, in fact, let's discuss that because it's a very short discussion. If I told you the returns, what's the best possible what's the best portfolio? What is it?
Yeah, put it all to the best one. Put all to the best one.
Thank you. You put it all in the best one. So you find, if someone tells you, happens to reveal to you what the what the returns are, it's extremely simple. You simply put EK, where K is an index corresponding to whichever one had the highest return. Okay. So that's the discussion of deterministic finance. It was a short one. So the interesting part is this: it's a random variable. So it's actually, the return is actually a random variable. So it's a random variable here. And it's got, and you can get much more sophisticated, but the basic one goes like this. So P is a random variable, and therefore P transpose X, that's the total investment return, is a random variable. Okay? And now, obviously, you want it large. Well, what does it mean to say a random variable is large? By the way, there's tons of ways to say a random variable is large. Okay, lots. I mean, maybe the simplest one is say its expected value is large. But then you say, well, now wait a minute, though, because it could have huge variance or whatever. You could say the probability, its 90th quantile is large. Its 10th quantile is large. You could say all sorts of things. There's many, many ways to do this. Actually, all of this comes down to this multi-objective stuff. So, all right. But really the simplest thing that makes any sense at all is this, is you evaluate the expected return and the variance. Or you can take the square root of the variance and get standard deviation. That's sort of the minimum thing that makes any sense at all, would be this pair. And now you have a bi-objective problem, because everyone wants high expected return. And I was going to say everyone, but let's just say let's just say everyone. Everyone will take a lower risk over a higher one. And you can get into all sorts of philosophy about, concave utility functions and risk averse and blah, blah, blah. So I won't get into that. Although you can take whole courses on that in economics and finance and stuff. And there'll be lots of colorful fights about it and things like that. But anyway, let's just say that people are risk averse. So what that means now is you plot these things actually by two things. You'd look at the risk as measured by standard deviation of return. Of course, you can get much more sophisticated measures of risk. Right? You can have downside risk, value at risk, it goes on, probability of a disastrous return, and this goes on and on and on. But just the simplest measure is just variance. And then you have all sorts of long discussions about this. Like somebody would make the stunning, you ready for an amazing observation? How about this? Someone points out, yeah, we judge portfolios by risk, but it turns out, well, imagine what would happen if your return was much higher than you thought. Would you be unhappy or happy? And you'd say, well, let me think about that for a minute. I guess I'd be happy. And they go, see, then you don't care about, variance is the wrong measure of risk. You care about the downside variance. It goes on. So these are all totally obvious things, but let's just, and by the way, if you make any assumption about the distribution, like if it's Gaussian, then all these go away. So anyway, so let's just assume variance is a measure of risk here, or standard deviation. And what you'd do is you'd solve this problem. Sorry, I haven't said yet how to solve a multi-criterion problem, but this would actually be the Pareto optimal boundary. It looks like this because return you want high, and risk you want low. So we can make the good direction is this. That's up is higher return, and left is lower risk. So when you read these things, you have to flip everything around so you remember what's good. It's always good to have a little map that shows you which way is good, okay, in your mind. So that's good. And so that's the Pareto boundary here. And this is an example of just a simple little portfolio where as you walk along this, each of these is a portfolio. And you can see things like this. If you go down here somewhere, the only thing with 0% risk puts everything in X4. So X4 in this example we presume is a risk-free is a risk-free asset. In fact, it looks like it's a Swiss bank account because it has no interest or something like that. Okay, so but no, that's the allocation. Oh no, sorry, I was reading the wrong plot. Sorry, there it is. So there it is. It's something over there. So that's the risk-free interest rate. As your tolerance of risk moves up, you start diversifying. So if you draw a line here like this, and you start diversifying into the riskier assets. I guess they're ordered from risk-free to riskiest. And for example, up here, if you accept a standard deviation of 8%, then it looks to me like you invest nothing in T-bills. So you're out of your cash position, and you're investing a little bit in X3, a little bit in X2, and a little bit in X1. And then when you move up to, for example, this level of risk, you're investing 50-50 in the two riskiest assets and so on. So these are the pictures. You'll do plenty of these. Don't worry, just for fun. Okay. So now let me say something about how you actually, what does it mean to solve a multi-criterion problem? Actually, that's an interesting question. We all know what it means to solve a scalar problem. What does it mean to solve a multi-criterion problem? Well, there's many definitions. I mean, one is this. If that multi-criterion problem has an actual optimal point, then for sure solving means you better find it. So if there was actually, and it could happen. I mean, here in a finance problem, you could have something in a portfolio problem, you could have something where basically you have one asset basically beats all of the others. In fact, it beats it in both risk and return, for example. In which case, this would be a stupid problem. The Pareto optimal curve would be a single point. Everything else would be down and to the right, meaning that you can choose this portfolio, or if you wish, there are many portfolios to choose from, but all of them have both lower return, they have lower return, higher risk, and one of those inequalities is strict. So that's what it would mean in that case. It could happen. I mean, obviously doesn't happen in practice, but that could happen. Okay. Now the other meaning is something like this. You could define the semantics of solving a multi-criterion problem as producing a Pareto optimal point. That's another meaning for what it means to solve it. Or an interesting one is actually quite interesting. One would be to produce one or more, or you want a method for exploring the Pareto optimal points. That's actually probably what you want when you say how do you solve it. So most methods for solving multi-objective problems will have some parameters or a joystick in them that would allow you to move around on the Pareto optimal surface, and which would be called exploring the Pareto optimal surface and that kind of thing. So I'm just saying you should expect that. There should be a joystick or something like that that allows you to move around on it. Okay, so classic method, probably hundreds of years old, scalarization. How does that work? In the general case, actually, it's quite elegant. It works like this. You choose a positive vector, positive in the dual cone. Okay? In the dual cone. Now, you might remember this. When we looked at it, it was completely context-free and had no actual practical meaning, and so you probably ignored it. But one way to say that f0 of x is k convex, one condition for that is the following. It's that lambda transpose f0 of x should be convex. That's a scalar function. It's a convex function for all lambda in k star in the dual cone. So that's one way to say it. In particular, this is a scalar convex optimization problem. Okay? By the way, this has already said something. In the case of multiple criterion, we'll see it's something very simple. It's a positive weighted sum of the objectives. You know, everybody knows that. You want to minimize a bunch of things, you put positive weighted sums and you wiggle the weights around to change the trade-off. That's obvious. This is much less obvious when we get to like matrices. You want to minimize, for example, estimation error covariance? It says take a positive definite matrix, you know, lambda, and minimize trace lambda sigma. That's what it says. This is not obvious, just to let you know. So, okay, so here's what happens. This is a general problem, non-convex, and here's what is really happening. It basically, and you can easily show any optimal point for this traditional scalar any optimal point for this is Pareto optimal for the original problem. Okay, so for example, that's convex or otherwise, makes no difference. Okay, so for example here in this problem, if you take a lambda like this and you minimize this, it basically says you go as far as you can in this direction, and you might find that point right there. That's Pareto optimal. Okay? Now, lambda, then by wiggling lambda, you're changing the slope here. And it says, for example, you can get this point. Now, what's very interesting here is that this point right here is Pareto optimal, but you cannot get it by any choice of lambda. It's actually, well, it's shadowed. You see, it's sort of like this, right? There's no way to get it. Now, you look at that and you realize the pathology there is non-convexity. So you should expect that in a convex problem, that's going to go away. And I'm not going to go into some technical details here. It having to do with on the boundary issues. So basically, if you relax this to lambda being positive semi-definite, you can have solutions that are not Pareto optimal. Okay? And not only that, there are Pareto optimal points which are not the solution of this, but they're sort of on the boundary, and they're just boundary issues, and I'm not going to, this is discussed in the book, and I'm not going to go into that. But that's the picture. Now, if you have a multi-criterion problem, this is very concrete, very simple. Lambda transpose times this is just you make a weighted sum objective, positive weighted sum objective. By the way, very important they be positive. Okay? Well, how do you do that? Well, I could put lambda 1 times this plus lambda 2 times that. They're both positive. But you know, without loss generality, I can make lambda 1 1. In fact, gamma here is lambda 2 over lambda 1. So that's what this is here. Okay? And then this would give you a least squares problem. This is called Tikhonov regularization. It's got other names and things like that. And then in more specific context, it would be all sorts of things. Instead of maximum likelihood, this would be MAP, or maximum a posteriori probability or something, an estimation. So this is something you see all the time. And here, as you vary gamma, you are varying the slope here, like this, and you will trace out these points exactly. Actually, you won't quite trace out that closed point there, and you won't quite get this one here with this scheme, I believe. But you'll get everything up to it. And so, except for some boundary points, in this case, you will trace out the Pareto optimal curve. It's a bi-objective problem, bi-criterion problem, so it's a curve. By the way, in the more general case, people refer to it as the Pareto optimal surface. Okay? So that would be that. Okay. And this is kind of obvious, if you have a circuit design and you minimize, the power, plus 0.7 times the delay plus 1.8 times the area, right? Then you're going to get a Pareto optimal design. If you want to explore, if you want to wiggle around on the Pareto optimal design, you change the weights. And it's kind of obvious how you change the weights. Actually, the choice of weights relates to our very next topic, which is duality. But for now, the weight, you can think of the weights as simply a joystick that moves you along the Pareto optimal surface. So that's the right way to do it. So if you go back to the risk-return trade-off, now I can tell you how those plots were obtained. They were obtained as follows. We minimized. That's the negative return. Yeah, I don't like it that way. Let me just go ahead and write it in the way that's more natural. We maximized this minus that. And I varied lambda from very small to very large. And I solved this QP for each value. And that's how I got the curve. Every one of those is risk-return Pareto optimal. And in fact, this gets you every one in the convex case. By the way, this has a name. This is called the risk-adjusted return. That's the average return. And now you penalize the return by some adjustment for risk. And then you would say something about gamma is your risk aversion parameter. Because it tells you how much mean return are you willing to give up for variance in your total return. So that this would be a risk aversion parameter. For us, it's a weight. It's in the dual cone of R2. That's R2 plus, which is R2 plus. It's a weight that simply weights variance versus return, period. That's all it is. So that's that. OK, so this finishes our whirlwind tour, very fast tour through optimization problems. You should have read chapter 4 by now. And you should read, of course, the CVX user's guide for that. And you can, hopefully they fit together. They should be coherent, in fact. So well, I hope they're coherent. If they're not coherent, let us know. We're by no means done. The rest of the class, every homework, no exception, you will see problems where you will formulate them as convex problems. You'll do numerical solutions. You'll work out more theory as we do it. So we are, although in some sense we've kind of finished our first coverage of problems, we do problems from now on, period, in applications and things like that. We're going to enter a new topic, which is actually sort of our last sort of theoretically oriented topic. There will be some others later, but this is a very important one, and it's duality. It relates exactly to these weights. And I'll just say a little, I'll start on it. This is in chapter 5. You should start reading chapter 5. OK. So we'll talk about duality is a very interesting topic. It's interesting theoretically. It turns out it has extremely interesting computational implications. It also turns out it is extremely important in all practical cases. So whenever you use optimization, you have to be aware of duality. And by the way, it's not just a theoretical thing. Although if you randomly search in the literature on duality, you'll imagine it's just something that people who do theory worry about. It's immensely practical, and we'll see that into it. Oh, you know what? You know what I want to do? Actually, there's something I forgot. I pushed it on a stack and didn't come back to it. I want to come back and say something about multi-criterion optimization versus scalar. Okay, and I just wanted to put them all in the common parent. So the common parent of scalar, so let's just put this over here. The common parent of scalar and multi-criterion optimization is this. If you want to put them on a common footing, you would introduce a concept called the hardness of a constraint. Okay, so that would be the word used, and a constraint that is infinitely hard, or let's say an objective that's infinitely hard. I mean, the problem is constraint already means hard, and objective already means soft. So let's call them objectives, but let's imagine let's call them functions. There we go, functions. So f0, f1, and so on. We're going to call them functions. An infinitely hard constraint. So you can do the concept of hardness by plotting your irritation versus the value of fi of x. Okay? So here's 0. That means you're not irritated at all. And the semantics of the objective your plot looks like that. That's your irritation. I mean, that's your irritation. I guess this means you're pleased. Okay? And this says basically the following. It says that you can make f0. I mean, f0 can be if it has to be large, it has to be large. It irritates you, but if it has to be large, it has to be large. So this would be a soft irritation function, right? So that's the picture there. Now, you can also be pleased. And if you had a choice between 2 points, one of which was sort of here and one was here, you'd prefer that because you're lower and it means you're less irritated. Everyone see this? Okay. So, oh, by the way, suppose you wanted to change this irritation function. What irritation functions work right away with convex optimization, just instantly? I mean, if this was your irritation, let me draw an irritation function and you see if you like it. How about this? Okay, and down there. That's my. And then someone says, well, why? And you go, not a problem. If this is the area, I always like things to be smaller, always. But you know what? When things start getting bigger than some threshold, it starts irritating me superlinearly. That's what this is. Can I express this as a convex optimization problem? I can, because I would simply take this function of f0. This function is convex and it is increasing, and therefore I can do that. Okay? So, of course, it's the same as the other one, but nevertheless, then the objective value would match yours. Okay, so this is the canonical irritation function for an objective. Now, let's draw the canonical irritation function for a constraint. For a constraint, the canonical irritation function looks like this. It's along the axis, so I kind of have to draw it that way. Okay? That's 0. That's your canonical irritation function. It basically says if, let's say in a classical problem, if f3 of x is less than or equal to 0, it doesn't irritate you at all. By the way, it's also true in the semantics of the basic problem that a smaller value of f3 means nothing to you. Absolutely nothing. Now, by the way, you might find someone in practice say something like, oh no, I'd prefer a smaller, but the actual semantics of the base optimization problem says that f3 of x equals 10 minus 10 to the minus 9, right, and equal minus 100 are equal for you. In any case, this is by no means any better than that. They are both feasible, end of story. That is the semantics of a hard constraint. Okay? Now, by the way, if you then hear people saying like, oh, no, I'd prefer this because then you see like I have this like margin and stuff and like this thing, boy, you just breathe on the system and you know, then it means your formulation is all wrong. If you prefer this, you better say so. Okay? So the point is, but the straight semantics is that is the same as that. And by the way, this and this are also equally and infinitely irritating. They're totally unacceptable. And here, you can't say, oh, come on. I just barely, you know. Now, as a practical matter, you know, you might argue. And in fact, if you look carefully at what numerical solvers will return, I mean, obviously, they'll return things that, for round-off reasons, might violate things slightly. I mean, but I think that's different from, but anyone who asserts that there's any difference between these, it means that you haven't formulated the problem. So basically, all of this, the common parent is the following, is that you look, this is sort of a very general thing where you have every constraint has a certain softness and hardness. And if you're willing to label all the, sorry, I think we call them functions, all the merit functions, or I don't know, whatever you want to call it. If you're willing to label all of them except one as absolutely hard, and one is soft, then you have a classical optimization. I mean, then you have a classical problem. Of course, that never really happens. I mean, you know, so you'd have a multi-criterion one. If you label all of them as soft, you have a multi-criterion one. And what really happens, I mean, it's totally obvious, is that some constraints are non-negotiable, and others maybe are. And they might be negotiable to different, and you might even have weird things like you could say, well, you know, you see this third this power constraint or whatever. Actually, if the power goes up to 2 watts, everything is fine because I can use this. I mean, actually, I like less power, but I can go up to 2 watts with this package. You go above 2 watts, boy, that's not good. If we have to, we have to. The whole project might not be feasible or something like that. There's more other packaging. It's more expensive, and we can talk about it, but only if we have to. So the real irritation functions might look something like this. For a constraint, it might look something like this. This would be kind of a real one, like that. Okay, with a small, and that basically says, do not violate this thing. But you know what? All other things being equal. Yeah. Yes, I have a slight preference for things being smaller. Okay. And that's why. Anyway. So all right. So I think that's the. So you can imagine. I mean, actually, there's actually very interesting issues involving user interfaces and things like this about how you should do this. Anyway, and people think you can imagine all sorts of. Anyway, I'll stop there. This is all in optimization modeling. The important part is that any of these schemes you can imagine can easily be represented and then and solved in an appropriate sense by some kind of scalarization. So that's how these work. So, okay, so that's all I want to say about that. Let's get back to duality, and I'll just say a little. Maybe I'll just say a little bit about it. So it's Lagrange duality, which we'll see it in a bit. And I'll just say a little bit about what it's used for and all that kind of stuff. So. Hopefully this will demystify the often mystical Lagrange multipliers, which is generally taught as a behavior in an advanced calculus class. So this will completely demystify it. That'd be the first thing. Then actually it's got a lot of interesting things. In fact, what it's going to do is it's going to end up producing from, actually this is very interesting, from any optimization problem. It will produce a convex problem, which is called the Lagrange dual. Okay, it's going to be so. Start with a non-convex problem, you'll get a Lagrange dual, which is convex. We can solve convex problems. I mean, roughly speaking, we can solve them. Okay, that Lagrange dual problem is actually going to give a bound on the optimal value of that original problem. Okay, if that original problem is convex, it's going to be a sharp bound. I mean, there's some conditions, but it's going to be a sharp bound, and it's going to be very interesting because it's going to have to do with, it's going to give you alternative methods for solving that problem. It's going to give you all sorts of interesting things. But it's also going to be extremely interesting when the original problem is non-convex. The original problem is non-convex and possibly a hard problem. Then, meaning one you can't solve efficiently. So it'll be a hard problem. It'll be a combinatorial problem or something like that. That'll be the original problem. We'll form a Lagrange dual. It's going to be a convex problem. We can solve it. And you're going to get bounds on that original problem. Okay? And you'll get cheaply computable bounds. And all sorts of cool things can happen. For example, it can happen that for that particular problem, those bounds are sharp. That happens. I mean, of course, in a very few number of cases. And in which case, you could hardly say the original problem is hard, because now you have a simple method to solve it. But we'll see a few cases where that actually happens. So that's a case where a problem that looked hard, by forming a Lagrange dual and then doing some extra math to show that in fact the bound is sharp, actually is solved by convex optimization. By the way, we're going to see there are going to be lots of those. Okay. Well, anytime a problem someone says is easy, and it's not posed as a convex problem, it's likely that in fact it's because the Lagrange dual is sharp. So that's true for many combinatorial problems, also of other things. Okay. Now the other thing that can happen is you can get a bound on a problem not, of course, known to be hard, but suspected to be hard. And there's amazing things. People have recently proved things like that there'll be a semi-definite programming Lagrange dual of a hard combinatorial problem. And they've proved things like specific ones, like max cut, for example. When you solve this Lagrange dual, the bound is never more than 13% off. Okay, just crazy things like this. That gets the complexity theorists all excited, and indeed that result got them very, very excited, as you can imagine, right? But it also, as a practical method for generating suboptimal solutions of that problem, these things can also be fantastically useful. So anyway, so that's our next topic. It's going to be essentially the last sort of core theoretical topic in the class, and I guess we'll start in on that next time. Good.